Hi, this is Schwartz from MasterMathMentor.com. This is video BC01. The topic is LHospitals Rule, and it covers the BC manual pages 1 through 4. In AB Calculus, we covered LHospitals Rule for indeterminate forms. It made the limit procedure that we learned in the beginning of the course so much easier. We start BC Calculus with a review of that material, as well as examining other indeterminate forms not in the AB curriculum. L'Hopital's rule, which was named after the 17th century French mathematician Guillaume de L'Hopital, allows us to evaluate limits involving indeterminate forms. An alternate spelling is L'Hopital with a circumflex O. L'Hopital's rule is amazing in its simplicity. It says that if A is a real number, infinity or negative infinity, then if the limit as x approaches a of f of x over g of x is equal to 0 over 0, or the limit as x approaches a of f of x over g of x is equal to plus or minus infinity over plus or minus infinity, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. We call 0 over 0 and infinity over infinity indeterminate forms. Students sometimes confuse L'Hopital's rule with the quotient rule. They are completely different. The quotient rule is taking the derivative of f of x over g of x, while L'Hopital's rule is concerned with taking the limit as x approaches a of f of x over g of x. And that means that we take the derivative of the numerator over the derivative of the denominator. In the following problems, you are to use L'Hopital's rule to find the limit. In number 1, we have the limit as x approaches 2 of 3x squared minus 7x plus 2 all over x minus 2. Our first step always is to plug in, and we get 0 over 0. That's indeterminate, so we apply L'Hopital's rule and get the limit as x approaches 2 of 6x minus 7 over 1. Plugging in, our answer is 5. 2 involves some algebra. The limit as x approaches negative 3 of x plus 3 all over the square root of x squared minus 5 minus 2. Plugging in, we get 0 on top, and on the bottom we get the square root of 4 minus 2, which is 2 minus 2, which is 0. So L'Hopital's rule can be used. The derivative of the numerator is 1. The derivative of the denominator is 1/2 x squared minus 5 to the negative 1/2 times 2x. We can bring the square root to upstairs and get the limit as x approaches negative 3 of the square root of x squared minus 5 all over x. Plugging in negative 3, we get negative 2/3. L'Hopital's rule can be used repeatedly in problems. 3 and 4 illustrate that. Number 3 reads, the limit as x approaches negative 2 of x cubed plus x squared minus 8x minus 12 over x cubed plus 8x squared plus 20x plus 16. Plug in negative 2 and you get 0 over 0. So applying L'Hopital's rule, we get the limit as x approaches negative 2 of 3x squared plus 2x minus 8 over 3x squared plus 16x plus 20. Plug in negative 2 again, and again we get 0 over 0. So we apply L'Hopital's rule one more time. The limit as x approaches negative 2 of 6x plus 2 over 6x plus 16. Now we get negative 10 over 4, or negative 5/2. Number 4 reads, the limit as x approaches 1 of x cubed minus 2x squared plus x over x cubed minus 3x squared plus 3x minus 1. Plug in 1 and we get 0 over 0. So applying L'Hopital, we get the limit as x approaches 1 of 3x squared minus 4x plus 1 over 3x squared minus 6x plus 3. Again, we get 0 over 0. So we apply L'Hopital one more time, and the limit as x approaches 1 of 6x minus 4 over 6x minus 6. We get 2 over 0, which means that the limit is undefined or infinite. Repeated use of L'Hopital's rule also works very well with trig functions and exponentials as well as natural logs. In number 5, we're interested in the limit as x approaches 0 of cosine x minus 1 over x squared minus x. Plugging in 0, we get 1 minus 1 over 0 minus 0, or 0 over 0. So applying L'Hopital's rule, we get the limit as x approaches 0 of negative sine of x over 2x minus 1, getting 0 over negative 1, or 0. Number 6 reads, the limit as x approaches 1 of natural log of x minus x plus 1 over e to the x minus ex. Plugging in 1, we get 0 minus 1 plus 1 over e minus e, and that's 0 over 0. We then use L'Hopital's rule and get the limit as x approaches 1 of 1 over x minus 1 over e to the x minus e, which is 1 minus 1 over e minus e, which again is 0 over 0. Rather than get rid of the complex fraction, we will just apply L'Hopital's rule one more time to get the limit as x approaches 1 of negative 1 over x squared over e to the x. And plugging in 1, we get negative 1 over e. Number 7 reads, the limit as x approaches 0 of 2 sine x minus sine 2x over sine x minus x cosine x. We first plug in 0 and get a 0 upstairs and a 0 downstairs, and we get the indeterminate form 0 over 0. So carefully applying L'Hopital's rule, we get the limit as x approaches 0 of 2 cosine x minus 2 cosine of 2x over cosine x plus x sine x minus cosine x. Plug in and we get 2 minus 2 over 1 plus 0 minus 1, or 0 over 0. So we apply it again, and we get upstairs negative 2 sine x plus 4 sine 2x over x cosine x plus sine x. When we plug in 0, we get 0 plus 0 over 0 plus 0, or 0 over 0. So, one more time, the limit as x approaches 0 of negative 2 cosine x plus 8 cosine 2x all over negative x sine x plus cosine x plus cosine x. And plugging in 0, we get negative 2 plus 8 over 0 plus 1 plus 1, which is 6 over 2, or 3. After all that work, you may want to confirm your results graphically. L'Hopital's rule can also be used with limits as x approaches infinity. Number 8 reads, the limit as x approaches infinity of 1 minus 4x minus 5x squared over 3x squared minus x minus 4. Plugging in infinity, we get negative infinity over infinity. So we apply L'Hopital's rule, taking the derivative of top and bottom, getting negative 4x minus 10x over 6x minus 1. Plugging in infinity, we still get negative infinity over infinity. We then apply L'Hopital's rule one more time, and we get the limit as x approaches infinity of negative 10/6, which is negative 5/3. Of course, a far easier way to do this is to look at the highest power terms and their coefficients. Since the highest power is x squared in both top and bottom, the limit is negative 5/3. However, that method will not work in number 9, the limit as x approaches infinity, of 4x squared minus 5x plus 2 over e to the 5x plus natural log of x, because our denominator is not a polynomial. So we plug in infinity and we get infinity over infinity. And we now use L'Hopital's rule to get the limit as x approaches infinity of 8x minus 5 over 5e to the 5x plus 1 over x. Plugging in infinity again, we still get infinity over infinity. We then use L'Hopital's rule one more time, and we get upstairs an 8, and on the bottom 25 e to the 5x minus 1 over x squared. And the limit as x approaches infinity of that expression is 8 over infinity, which is 0. So in review, we have our basic indeterminate forms. Limits in the form of 0 over 0 and infinity over infinity. Once our expressions are in that form, we can use L'Hopital's rule to hopefully simplify it. Here are the other indeterminate forms, and the conundrum in trying to use logic to figure out what they should be. First, 0 times infinity. We know that 0 times anything is 0, but infinity times anything is infinity. Infinity minus infinity. You might expect that infinity minus infinity equals 0. After all, any number minus itself is 0. But if you subtract the number of odd natural numbers from all the natural numbers, you are left with all the even natural numbers, which is also infinite. 1 to the infinity. 1 to any power you expect to be 1, right? Not so fast. Infinity to the 0. You would expect that infinity raised to any power would be infinity, but anything to the 0 power equals 1. 0 to the 0. 0 to any power is 0, but any power to the 0 equals 1. There really is only one hard and fast rule when you are working with infinity. All rules go out the window when playing with infinity. Don't expect logic. L'Hopital's rule works with the indeterminate forms 0 over 0 or infinity over infinity. When we work with the other indeterminate forms, infinity times 0, infinity minus infinity, 1 to the infinity, infinity to the 0, or 0 to the 0, realize that we must change those forms into 0 over 0 or infinity over infinity to use L'Hopital's rule. This next section will show you how to do that. In studying our other indeterminate forms, we first look at the form infinity times 0. We utilize the fact that expressions in the form of f of x times g of x can be written as f of x over 1 over g of x. Rarely do we do a procedure like that. It seems we are making the expression harder rather than easier. But this opens the door to L'Hopital's rule. Number 10 reads the limit as x approaches 0 from the right of x squared natural log of x. When we plug in, we get 0 times infinity. Actually, 0 times negative infinity. This becomes the limit as x approaches 0 from the right of natural log of x, and we write x squared as 1 over x squared. Plugging in, we now get infinity over infinity. So using L'Hopital's rule, we get the limit as x approaches 0 from the right of 1 over x over negative 2 over x cubed. Inverting the denominator, we get the limit as x approaches 0 from the right of 1 over x times negative x cubed over 2, which is the limit as x approaches 0 from the right of negative x squared over 2, and our answer is 0. 11 reads the limit as x approaches infinity of x times sine of 1 over x. Plugging in, we get infinity times sine of 1 over infinity, which is the sine of 0, which is 0. So this becomes the limit as x approaches infinity of sine of 1 over x over 1 over x. Plugging in, we get 0 over 0. So this becomes the limit as x approaches infinity, utilizing L'Hopital's rule, of cosine of 1 over x times negative 1 over x squared over negative 1 over x squared. Those terms cancel out, and we're left with the limit as x approaches infinity of cosine of 1 over x, which is the cosine of 0, which is 1. I like to think of problems in the form of infinity times 0 as a tug of war. Sometimes the infinity wins, sometimes the 0 wins, and sometimes the answer is in the middle. The next indeterminate form is infinity minus infinity. We use the fact that expressions in the form of f of x minus g of x can be written as the difference of two fractions, and then get a common denominator. So the limit as x approaches pi over 2 of secant of x minus tangent of x can be written as the secant of pi over 2 minus the tangent of pi over 2, which is infinity minus infinity. We write these expressions as fractions. The limit as x approaches pi over 2 of 1 over cosine of x minus sine of x over cosine of x. And now with a common denominator, the limit as x approaches pi over 2 of 1 minus sine of x over cosine x. That is 0 over 0. So we're now free to use L'Hopital's rule and get the limit as x approaches pi over 2 of negative cosine of x over negative sine of x, and the answer is 0. Number 13 reads the limit as x approaches 0 of 1 over e to the x minus 1 minus 1 over x. Plugging in, we get the limit as x approaches 0 of 1 over 0 minus 1 over 0, which is infinity minus infinity. So we now work to get a common denominator, which is x times the quantity e to the x minus 1. This becomes the limit as x approaches 0 of x over x e to the x minus 1 minus e to the x minus 1 over x quantity e to the x minus 1. And that gives us limit as x approaches 0 of x minus e to the x plus 1 over x quantity e to the x minus 1. And plugging in, we get 0 over 0. So using L'Hopital, we get the limit as x approaches 0 of 1 minus e to the x over x e to the x plus e to the x minus 1. That still gives us 0 over 0. So we utilize L'Hopital again, getting the limit as x approaches 0 of negative e to the x over x e to the x plus e to the x plus e to the x. And our answer, unbelievably, is negative 1/2. The graph of 1 over e to the x minus 1 over x confirms the fact that the limit of that expression as x approaches 0 appears to be negative 1/2. Even though our form was infinity minus infinity, we get the answer of negative 1/2. As I said, don't expect logic when it comes to infinity. Number 14 reads the limit as x approaches 0 of cosecant of x minus 1 over x. That is infinity minus infinity. So we first write cosecant of x as 1 over sine of x, and we have the limit as x approaches 0 of 1 over sine of x minus 1 over x. We get a common denominator, x sine of x, and we have the limit as x approaches 0 of x minus sine of x over x sine of x. Plugging in, we get 0 over 0. So utilizing L'Hopital's rule, we get the limit as x approaches 0 of 1 minus cosine of x. And on the bottom, using the product rule, x cosine of x plus sine of x. And we still get 0 over 0. Then we use L'Hopital's rule one more time, and we get limit as x approaches 0 of sine of x over negative x sine of x plus cosine of x plus cosine of x. And plugging in, we get 0 over 2, and our answer is 0. Number 15 reads the limit as x approaches 0 of 4 to the x over x minus 2 to the x over x. Plugging in, we get 1 over 0 minus 1 over 0, which is infinity minus infinity. So we have a common denominator, and we can write this as the limit as x approaches 0 of 4 to the x minus 2 to the x over x. Plugging in, we get 0 over 0. So, utilizing L'Hopital's rule, we get the limit as x approaches 0 of the derivative of 4 to the x is 4 to the x natural log of 4, and the derivative of 2 to the x is 2 to the x natural log of 2. So our answer is natural log of 4 minus the natural log of 2, and that can be written as the natural log of 4 over 2, or the natural log of 2. The graph confirms this unexpected result of this form infinity minus infinity. Natural log of 2 is approximately equal to 0.69. Limits in the form of 1 to the infinity, infinity to the 0, and 0 to the 0 are all handled in the same way. These are in the form of y equals f of x to the g of x. We perform logarithmic differentiation. That is, we take the natural log of both sides. We then express the right-hand side as a fraction in the form of 0 over 0 or infinity over infinity. We use L'Hopital's rule to determine a limit L, and then realize that this limit L represents the natural log of y, so y is equal to e to the L power. 16 reads the limit as x approaches infinity of x to the 1 over x power. We call that y, and when we plug in, we get infinity to the 0, which is indeterminate. So we take the natural log of both sides, and we get the natural log of y is equal to the limit as x approaches infinity of 1 over x times the natural log of x. And the right-hand side is now in the form of 0 times infinity. So we will now write this as natural log of y equals the limit as x approaches infinity of the natural log of x over x. And this is infinity over infinity, allowing us to say the natural log of y is equal to the limit as x approaches infinity of 1 over x. This is L'Hopital's rule, and that is equal to 0. So we have natural log of y is equal to 0, but we want y, so y is equal to 1. Number 17 reads the limit as x approaches 0 of x to the x. When we plug in, we get 0 to the 0. So y is equal to the limit as x approaches 0 of x to the x, and we get natural log of y is equal to the limit as x approaches 0 of x natural log of x using our log rules, and that's in the form of 0 times infinity. So we have to transform the right-hand side to infinity over infinity, and the way we do that is we write x as 1 over x. So we have the natural log of y equals the limit as x approaches 0 of the natural log of x over 1 over x, and now we have infinity over infinity. This allows us to use L'Hopital's rule, and we get the natural log of y equals the limit as x approaches 0 of 1 over x over negative 1 over x squared. We can now flip the denominator and write this as the limit as x approaches 0 of negative x squared over x, which is the limit as x approaches 0 of negative x, which is 0. So again, natural log of y equals 0 and y equals 1. Number 18 reads the limit as x approaches 0 from the right of x to the sine of x. Plugging in, we get 0 to the 0, and therefore we write this as y is equal to the limit as x approaches 0 from the right of x to the sine of x. Taking the natural log of both sides, we get the limit as x approaches 0 from the right of sine x natural log of x, and the form is now 0 times infinity. We can write sine of x as 1 over cosecant of x, and now we have natural log of y is equal to limit x approaches 0 from the right of natural log of x over cosecant of x, still getting infinity over infinity. We apply L'Hopital's rule, and our form is now 1 over x over negative cosecant x cotangent of x, and again we get infinity over infinity. Getting rid of the complex fractions, changing sine, cosecant to sine and cotangent to tangent, we get the limit as x approaches 0 from the right of negative sine x tangent of x over x, and now we have 0 over 0. So L'Hopital's rule one more time, and we get limit as x approaches 0 from the right of negative sine of x, secant squared of x, minus tangent of x, cosine of x. Plugging in 0, we get 0. So the natural log of y is equal to 0, and y is equal to 1. 19 is similar to 18. The limit as x approaches 0 from the right of sine of x raised to the tangent of x. Again, that's in the form of 0 over 0, so we write this as y is equal to the limit as x approaches 0 from the right of sine of x raised to the tangent of x. We natural log both sides, and we get the limit as x approaches 0 from the right of tangent of x, natural log of sine of x, and now we have 0 times negative infinity. We write that as the limit as x approaches 0 from the right of the natural log of sine of x over cotangent of x, and now we have infinity over infinity. We now write the right side as the limit as x approaches 0 from the right of cosine of x over sine of x all over negative cosecant squared of x using L'Hopital's rule. And changing everything to sines and cosines, our right-hand side is cosine x over sine of x times negative sine squared of x. And therefore we have the limit as x approaches 0 from the right of negative sine of x, cosine of x, which is 0. Again, remember that this is the natural log of y equaling 0, and therefore y is equal to 1. Number 20 reads the limit as x approaches infinity of x plus 1 over x to the x. Our first step is to plug in infinity, and we get 1 to the infinity, which is not 1, it's indeterminate. So we call the expression y. Taking the natural log of both sides, we get on the right side the limit as x approaches infinity of x, natural log of quantity 1 plus 1 over x, and that becomes infinity times 0. We now write the x as 1 over x, and our right side is the limit as x approaches infinity of the natural log of 1 plus 1 over x all over 1 over x, and that becomes 0 over 0. We now apply L'Hopital's rule, and we get 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x, which is negative 1 over x squared, over the derivative of 1 over x, which is negative 1 over x squared. And these two terms cancel out, so we're left with the limit as x approaches infinity of 1 plus 1 over x, which is 1. So the natural log of y is equal to 1, and therefore y is equal to e. This is an unexpected but important result. The limit as x approaches infinity of x plus 1 over x raised to the x is the definition of e. It doesn't seem logical. We're talking about 1 1/2 squared, 1 1/3 cubed, 1 1/4 to the fourth, and 1 plus 1/10 raised to the 10th, 1 plus 1/millionth raised to the millionth. You would think that x plus 1 over x is getting very close to 1, and 1 to any power is 1, and yet the answer is e. We can confirm that by looking at the graph out to from 0 to 50, and notice how the graph becomes asymptotic to e, which is 2.71. Finally, 21, the limit as x approaches 0 of e to the x plus x raised to the 1 over x. Plugging in 0, we get e to the 0 plus 0 to the infinity, or 1 to the infinity. So we call this expression y. Taking the natural log of both sides, we get the limit as x approaches 0 of 1 over x times natural log of e to the x plus x. Plugging in 0, we have a 0 in the denominator and natural log of 1, which is 0 in the numerator. So we apply L'Hopital's rule, and we get the limit as x approaches 0 of e to the x plus 1 over e to the x plus x. And when we plug in 0, we get 2. So the natural log of y is equal to 2, and therefore y is equal to e squared. I suggest you confirm that on the calculator.